Inferences from two samples. Here we're going to be doing some hypothesis testing where we're comparing two means from independent samples to each other. We're going to again be using the p-value method and the critical value method. So first, a comment on independent versus dependent samples. Two samples are said to be independent if the sample values from one population are not related to or paired with the sample values from the other population. So for example, measuring blood pressure of 40 randomly selected men and 40 randomly selected women, those would be independent samples. However, if we measured the blood pressure of 40 randomly selected married couples and compared the group of men to the group of women, those would be dependent samples because they're paired with each other. Okay, we're only going to be discussing independent samples here, so let's get started. For the p-value method first. The test statistic that we'll be using for our two independent samples is, since we're dealing with means here, is the student t-test statistic. And at first we're going to use x1 bar minus x2 bar, which is the sample mean for the first population minus the first sample minus the sample mean for the second one, and then subtract that from the population mean for the first group minus the population mean for the second group. Divide that by the standard deviation of the first group squared, the first sample group, squared, divided by its sample size, plus the standard deviation of the second sample squared, divided by its population size. Now, this is really cool. For these examples, the null hypothesis will always be mu1 equals mu2, which means in the numerator of our test statistic, mu1 minus mu2 is equal to 0. So our adjusted test statistic becomes x1 bar minus x2 bar over the square root of s1 squared over n1, plus s2 squared over n2. Okay, let's do a couple of examples. The mean tar content of a simple random sample of 25 unfiltered cigarettes is 21.1 milligrams with a standard deviation of 3.2 milligrams. The mean tar content of a simple random sample of 25 filtered cigarettes is 13.2 milligrams with a standard deviation of 3.7 milligrams. Test the claim that unfiltered cigarettes have a mean tar content greater than filtered cigarettes. Okay, same steps as we've been doing in previous methods. The first thing we have to do is identify the claim. If we let mu1 be our first group, the mean tar content of unfiltered cigarettes, and mu2 is the mean tar content of filtered cigarettes, then our claim is that mu1 is greater than mu2. Filtered cigarettes would have a greater mean content than the unfiltered. Opposite. The opposite of mu1 is greater than mu2 is mu1 is less than or equal to mu2. And from those two, we need to come up with our null and alternative hypotheses. So as I said a second ago, the null hypothesis will always be simply mu1 equals mu2, which leaves the claim, or the one without the equality sign, mu1 greater than mu2 to be our alternative hypothesis. The last thing we need to do is identify the significance level, and if you notice, if you reread this problem, it doesn't give us a significance level. So if you don't have a significance level given, the standard that we use is alpha is 0.05 for a significance level. Okay, regardless of whether we're using the p-value method or the critical value method, we always need to find the test statistic next. And to do the test statistic, we're going to use our formula that we had up a few minutes ago. So x1 bar, our first sample mean we have is 21.1, and x2 bar also is, 13.2. Our first sample standard deviation is 3.2 in the denominator, and the second standard deviation for the second group is 3.7. So plugging all that in and getting out our calculators, we have t equals 8.075. Okay, since we're using the p-value method here, we need to find the p-value that corresponds to a t equals 8.075. We can use our graphing calculators, we can use the student t-distribution chart, we can use an online calculation software. Regardless of what method we use, though, we do need the degree of freedom. We know this is a one-sided test, a one-tailed test, because it was a greater than. And we know the t-value, but to find the p-value, we need degrees of freedom. When you have two samples here, the degrees of freedom is the smaller of n1 minus 1 or n2 minus 2. In this particular example, both the first and the second samples are 25. So 25 minus 1 in each case gives us degrees of freedom of 24. Okay. If you look up the t-value of 8.075 in a one-sided test, a one-tailed test, degrees of freedom 24 and a 0.05 significance level, it's going to be off our table a little bit, but we do know that that p-value is smaller than 0.005. So if there were a couple of videos ago, I discussed in greater detail how to do that using a chart if you don't have access to technology. So if you missed that, go back a couple of videos where we talk about using the t-distribution table to find the p-value method, to find the p-value. Okay, our p-value is less than 0.005. Using the p-value method, we want to compare that to our significance level. So since our p-value is less than 0.005, it is much less than the significance level of 0.05. That means it's in the critical region, so we must reject the null hypothesis. And if you remember, the null hypothesis was that the two mean tar contents were equal. So the hypothesis that we can support would be the alternative hypothesis, which is our claim. There does appear to be enough evidence to support the claim that unfiltered cigarettes have a mean tar content greater than filtered cigarettes. Okay, let's do another example, and let's use the critical value method this time. Really similar steps, just different at the very last couple steps. So this one says the heights of a simple random sample of 9 supermodels gives a mean of 70 inches and a standard deviation of 1.5 inches. A simple random sample of 40 women who were not supermodels gives a mean height of 63.2 inches and a standard deviation of 2.7 inches. Use a 0.01 significance level to test the claim that the mean height of supermodels is no different than the mean height of women who are not supermodels. Okay. First, identify the claim. Let mu1 be the mean height of supermodels, and mu2 then would be the mean height of non-supermodels. To say that the mean height of supermodels is no different than the mean height of women who are not supermodels is to say that they are equal. So mu1 equals mu2 would be the claim. That means the opposite of the claim is mu1 is not equal to mu2. So we have a two-tailed test. Okay, the next thing we have to do is identify the null and alternative hypotheses. So null hypothesis, as always, mu1 equals mu2, and alternative hypothesis is that mu1 is not equal to mu2. And the significance level they gave us is 0.01. Okay, critical value method. Always have to start with the test statistic. So our x1 bar minus x2 bar are given, so that would be 70 for x1 bar mean, and 63.2 is our mean for the second group, or x2 bar. And our standard deviations are 1.5 and 2.7 respectively. So when we plug all those in, including N1 is 9 and N2, the sample size for the second one, is 40, we get a t-value of 10.343. Okay, determine the critical value, since we're using the critical value this time. The critical value is determined from looking at the significance level and finding its corresponding critical t-value. So using the t-distribution table, Remember, the degrees of freedom, we use the smaller of n1 minus 1 and n2 minus 2, which would be 9 minus 1 or 40 minus 1. Well, 9 minus 1 is 8, and 40 minus 1 is 39, so the smaller of those two is 8, so our degrees of freedom is 8. If we look at the t-distribution table, our critical values are going to give us t-values that are 3.355 positive or negative, so plus or minus 3.355. Those are the values we're going to compare to the test statistic. And our test statistic is much bigger than our positive critical value, which again puts us in the critical region, so we reject the null hypothesis. So remember that the null hypothesis was that the means were equal to each other. That claim we are rejecting. So since we're rejecting the null hypothesis, there is enough evidence to reject the claim that the mean height of supermodels is no different